Hello, people who are watching this video in the future. It's semester 1, 2023, and we are here in the Flinchy Lecture Theatre doing a revision seminar for DEs for engineers. And I've already had a big chat with people about what we're going to cover, and we're just going to try and do a bit of a what methods are there and what do they go with before we move on to some specific cases. All right, cool. Yes, I know I'm screen sharing. Okay. All right. All right. Let's see what we can do here. I'm going to need to sharpen my pencil again. Okay. Right. So before I do the overview of methods, we need to know what a differential equation is. Hopefully you're familiar with it by now after 12 weeks of this. But people might be watching this at the beginning of the course, so I'm going to say it now. I'm going to put the chat back up. Okay. So a differential equation is an equation that's got a derivative in it. That's basically it. But the purpose is to figure out an unknown function. An unknown function and the variables it depends on. And it's got derivatives in it. And the goal is find the function. That's the goal. So when someone says solve a differential equation, the answer at the end is like y equals formula involving x. That's the goal. So if you've got something that's got, you know, something ridiculous like this, which is not something you know how to solve in this course, the goal is y equals something involving x's. That's the goal. Now this is what I said back in Maths 1B as well, but it's important to know that this is still the goal. Okay. Sweet. Right. And the thing is, that's actually really quite hard most of the time. It's really quite difficult. Like you've got derivatives of a function you don't even know what it is, combined possibly with a variable or not. Like it's just hard. And this course is a catalogue of various different, really quite creative ways of trying to figure out how to do this. And most of those ways are of the flavour, what if the answer was like this? So that's the goal. Most methods are like what if the answer was like this? And then you do that supposal and say, what if, and you do some calculations and it turns out that actually the answer is like that after all, and yay, it works. But all of them are like that. And so it's a really useful way of organising your thinking about this course to say, where's the bit, in this method, where's the bit where we said, what if it was like this? Because at the end, then you need to be able to put it back together with the what is it like to be able to do it. And I'm going to keep, and that doesn't make any sense at the moment, but I'm going to keep talking about that as we go. There are some other methods at the end of the course with the transform stuff, which is not about that. And it is a whole different vibe. But the majority of us like this. And if you didn't have to do an exam on it, or assignments, it would be actually kind of interesting as a study in the creativity of mathematicians. So this is, or physicists sometimes, it's really cool, some of the things that they've tried. You go, that I would never have thought to do that. And isn't it amazing that it even works at all? Like there's some really cool things in there. And try to hold on to that a bit. Any maths course is about, not just about the maths, but about the mathematicians and you having to work with what mathematicians do in the rest of your life if you're going to go into a career in this area. You're going to have to work with what mathematicians do, and so it's sometimes useful to know how they think and appreciate that they are creative about these things is a nice thing to give you some grace when you work with them and they're being annoying. Okay, so there you go. Right, so there are two main flavors of differential equations that you have seen in this course. You have seen ordinary differential equations and you have seen partial differential equations. And you have seen systems of differential equations. Damn it, not enough room for both. Oh, I can put it in the middle. Yeah, that'll work. These are the three main types that you have seen. And an ordinary differential equation, well, a partial differential equation has got partial derivatives in it. I'm actually going to start there, actually. A partial differential equation has partial derivatives in it. And so having partial derivatives means that the function that we're trying to find, that goal function, is a function that has multiple variables as inputs. It's a multivariable function which is often called u, but it's sometimes capital T or it's sometimes a v or who knows what. It could be anything, but it's often called u. And the idea is that u is made by putting x's and y's, or possibly u is made by having x's and t's. There's lots of different options of how it could be done. But that's the situation in which it's in. I'm just going to move this down. The goal is to have a formula for u in terms of x and t or x and y or whatever it is. That's the goal. Okay, and it will have partial derivatives in it. So it might be something like that would be an x now, wouldn't it? Something like that, right? That's a partial differential equation because these are partial derivatives. And the point is that x and t are variables that are creating this function u, and we don't know what u is, but we do know how its partial derivatives are related to each other. That's a PDE. Feeling okay? Cool. You have been taught 2 ways of attacking a PDE. Technically 3. 3 ways of attacking a PDE. So the first way you were taught, anyway, there is one way that you've been taught, which was called separation of variables. And when you did separation of variables, the what if question was, what if u was made of 2 separate functions multiplied together? Did your lecturers use f and g?
Yes.
but sometimes they use capital X and capital T. Yep, just to mix it up. Cool. All right. And everything that you do flows from this assumption. And what you do is you don't just separate the function into two things multiplied together, you literally separate the differential equation into two separate differential equations. And so separate the PDE into two ODEs. So the reason that they taught you the PDE methods at the end is because you can't do it without knowing how to deal with ODEs. Yeah. And also, it usually turns out that you end up having to use Fourier series. Okay. Okay. With that, just that assessment of how PDE separation of variable solving goes. Yeah. So that is the big assumption. What if it was two separate functions multiplied together, and then you differentiate, you sub in, you separate into two different ODEs, and you solve one of them, and you sub the answer from one of them into the other, and then you get an infinite series, and lo and behold, it's got causes in it, and so it's a Fourier series. And so therefore, in order to solve separation of variables problems through this entire process, you have to know about how Fourier series work. And hence they've told you about Fourier series in the week before you did that stuff. All right, so that's the other thing that happens in differential equations, is that, like, what if the answer was written like this, means you have to know how different ways of writing functions work. And so in order to do this, we have to know, actually we end up with writing a function as a Fourier series as another way of writing a function, not just as a product of both of them. So just pointing it out, it's a thing. All right. The other methods you've been given are using the Laplace transform. And I'm pretty sure in at least one of the lecture, or at least one of the pages of the notes, they used a Fourier transform to do PDEs as well. Is that true? Yeah, of course they did. And these two are a whole different vibe of thing. The point of both of these things is to have an operation that you perform on functions that turns them into other functions that turns derivatives into multiplication. That's what they do. The whole point of this is that the Laplace transform of f dashed of t is s times the Laplace transform of f of t minus f of 0. It turns the derivative of a function into timesing by s. And the Fourier transform, like the complex one, f dashed of x usually in Fourier, isn't it? Is IW times the Fourier transform of f of x. That was in the most recent Mobius, so I can remember it off the top of my head. 1 week from now, no, I would have to look it up. Or I would have to try to remember it and then look it up, because that would make me better at remembering it. So the big point of the Laplace and Fourier transform methods is that it turns derivatives into algebra. And so instead of trying to integrate things, I'm going to solve equations instead. That's the idea behind them. And I am in awe of these people for thinking of this. What the hell? It's so clever. So clever that sometimes it's confusing, but also just really cool that this would even work as an idea. Yeah. So we have functions of functions that take functions in and spit functions out. And the act of doing doing derivatives before is the same as timesing by s after, or timesing by iw after, or whatever. I'm not going to go into details on that unless I probably will actually, because of what's on the board, but that's the idea behind them. So why would you choose to do one of them do these over this? Well, technically this is shorter, the Laplace transform thing. It requires slightly less work. And it allows you to deal with functions that don't start until later. Like this one will always be made of sines and causes or something, whereas this one, if there's a u in it, like that turns it on at a certain point, then the Laplace transform will make that appear all by itself. But in an exam, they're not going to get you to choose which of those processes to use for a PDE. I have never seen it happen ever in my 15 years of working at the Maths Learning Centre. No one has come back to me and said, they asked me to choose whether it was separation of variables or Laplace transform I should use. No, they just tell you. So please don't worry that in this course you have to make the decision yourself as to which one to do. Now, there may come a point in your life where you do have to make the decision yourself, but at that point in your life, you won't be examined on it and you can ask someone to help you. So it'll be okay. How are we feeling? Yep, oh, cool, that was a thumbs up, good. So that's PDEs. And this was like, all of this was like the last 3 weeks, 4 weeks? I don't know, the last bit. The bit of the course that I've had so many people tell me in the Maths Learning Centre that after this bit of the course started, they just suddenly felt like they couldn't do maths anymore. So if you're feeling that way, I can't take the feeling away, but at least I can make you feel like you're not alone. It's not just you. And that makes you feel slightly better. Like, you're not an idiot, it's just hard. Okay? So I want to say that to you. But you can make it easier on yourself. And I try my best in the revision seminars to do that. Okay, so that's PDEs. Sweet. ODEs. So ordinary differential equations come in multiple different flavors, and there are different approaches for different of those flavors. They come in flavors of order and linearness. So there are first order, and they have their own methods, and there are second order, and they have their methods too. And I don't know if I'm going to fit it all on this page, but I'll give it a go. So first order means that the only derivatives that appear are first derivatives. But second order can have first or second derivatives. They may not have any first derivatives, but to be second order, they have to have second derivatives. And technically, there's such a thing as third order ones and fourth order and blah, blah, blah. Okay, so first order DEs are the ones that you met in Maths 1B. And first order DEs have come in flavors of separable and linear. And if we're being creative, exact. All right. I'm pretty sure this is it. Could be wrong. I'm pretty sure. So these two we're in Maths 1B, and this one's new. We did exact, didn't we? Yeah. This one's new for engineering, for Ds for engineers. So separable ones are ones that can be written a certain way. I'm just going to do it as dy and dx, if that's okay. They can be separate. Actually, I'm not going to do that. I'm going to make more space. I'll come back to this later, okay? So we're in ODEs, we're in first order, and we're in separable. Okay, so separable DEs are ones that can be separated. You can get all the x's and dx's on one side and all the y's and dy's on the other, or whatever the variables actually are. It could be y's and x's, or t's and x's, or y's and t's, and whatever, thetas, and doesn't matter. But the point is that they can be done this way. So in my head, a separable DE is one that can be done this, that you can get to this point. Some function of y dy equals some function of x dx. And you started, that's a different function, sorry. You started with dy and dx equals something involving x's and y's. And if you're able to treat this dy and dx as if they were numbers and multiply both sides by dx, and factorize this out and divide by something to get to here, then it's separable. So the easiest way to tell if something is separable is to attempt to separate it. And it's called separable because you can separate the x's and the y's on either side. It's also called separable because technically you can separate this into something involving x's times something involving y's. Because otherwise you wouldn't be able to divide by the thing involving y's to get it to the other side. A really important thing to know about how to do separable equations is that the process that gets from here to here is all multiplication and division. You can't subtract to get from here to here. You can only divide or multiply. That is useful to know. So that's separable. And once you get to this stage, you integrate both sides and then you rearrange for y equals and you're good. Cool. And so you'll get something involving y equals something involving x with a plus c, and then you'll rearrange that for y equals something involving x. That's sort of what the working looks like. You okay with me writing the squiggles like that? Yeah, okay. So in my head, when I think of these things, I have a vague, I don't actually see pictures in my head, but I know where they are. I have this idea of the picture in my head of what the working is like and what things are in what spot in the working. And so this is, I'm trying to draw a picture of that. Now, at this stage, that's called an implicit solution, and this is called an explicit solution. An explicit solution says y equals function of x. An implicit solution just says something involving y equals something involving x. Or possibly something involving x's and or y's equals 0. Like an implicit solution is some sort of formula involving x's and or y's equals something. An explicit is y equals. So just warning you that there are some times in exams where they say, leave your answer in implicit form. In which case you can stop here and not go all the way to here. It's worth noting. Yeah, so that's separable. Linear is the other one. And linear first order ODEs can always be rewritten to look like this. The dy on dx or the dx on dt or whatever it is all by itself, not attached to anything else. That's important. Plus something in this spot equals something in this spot. I think they call it Q, or do they call it R? Probably doesn't matter what you call it. It's tradition to call the bit on that side R. They call it what? Oh, there's a P there and a Q there and an R there. Okay. Yeah, so it may not look like this to begin with. But if you can use multiplication and division and factorizing and stuff to make it look like this, where the dy and dx is all by itself, not attached to anything, there is the only other y in the entire equation is a single y all by itself, multiplied by possibly something involving x, and then everything else is over here. That's a linear first order dE. And once it is in that format, then you can solve it. It technically doesn't have to be in that format already to be able to solve it, it's just the quickest way. So that's linear. And it's really interesting when people learn this first, they don't know what to look for to tell if it's linear. And that's why I say this is on its own and there is only one other y. Okay, so it is totally possible for this not to have any x's in it. That's okay. It can be a 0, it can be the number 4. It's just not allowed to have any y's in it, that's all. And this px also can be just like the number 2 or just a minus. That's okay as well. Because the number 2 is a function of x, it just always produces the answer 2 no matter what x is, because there's no x there. So once it's in this format, and it has to be this format, and if there is a minus here, you have to include the minus as part of the px. That's really important. There's this really cool magic trick that they use, where they go, hey, I know something that has a dy on dx in one bit and a not dy on dx, just a y in another bit, and it's the thing that comes out of the product rule. If I had something times y, I'd have this derivative times y and this original times dy on dx. That's where the product rule is. So what they do is they engineer this to be a thing that came out of the product rule. So what's in their heads is thing times dy on dx. This is what they want, plus thing times y equals thing, where this is the derivative of that. That's the goal. I shall call this, I don't know, it's not the integrating factor. Actually it is, isn't it? Oh, cool. What did they call the integrating factor in this course? Mu? So what I would like is to have mu here and d mu on dx here, like that. That's the goal. Equals, I don't care what that is. And then this, is the product rule. So if I integrate it, I'll just get mu times y. And then I'll have to do whatever the integral of all of this stuff is, because I have to integrate both sides. It's it's just clever. Okay. So here's the thing. How the hell am I going to figure out what the mu is? And my favorite thing about it is that, look, see this mu, it got attached to the dy and dx. So I'm going to have to multiply by it to get to this stage. I'm going to have to times everything by mu. And that means that this has to be the derivative of mu. So I have to think of a function mu that when I differentiate it, all it does is attach the function px to it. Wow. And the correct answer for that function is, so here's the actual process now. I'm going to integrate px. So I'm going to do this. And I'm going to get an answer. I don't care about the plus c. That's going to be fine. It's not going to make any difference. And then I'm going to do my mu of x is e to the power of whatever that is. And that will do the trick. And then if I multiply everything by that, it will do the product rule. And I don't even have to worry about it. It'll work. That's the process. And this is our first thing in this course where they went, trust the process. They might have given you a proof, but then they went, trust the process. Okay. And the reason this works is that when you differentiate this, because of the chain rule, you'll get e to the thing times the derivative of the thing, and the derivative of that thing is p of x, and so it'll work. You'll get differentiating this function is the same as timesing it by p of x. And it's just so clever. I love it. I don't have to do it in exams, so that changes my opinion on it, of course. So that's linear first order DEs. Cool. And this is called an integrating factor, this thing here. So the short version is linear first order linear ODEs you do with an integrating factor. Separable ODEs, you separate them. And that is how you do them. And there is one last kind. Oh, stop. How are we feeling? Okay. There is one last kind of ODE which you've never seen before, and it goes like this. Exact ODEs. And an exact ODE looks like this. It has crap involving x's and y's and a dx, and crap involving x's and y's and a dy equals 0. If you can rearrange your equation to look like that, then it is, well, it's not exact yet. This is called a differential form of a differential equation. So just so you know, a dx is called a differential. So the two parts of a derivative, the dx and the dy, the name of those things is differentials. So that's why this is called differential form, because you've written it with differentials in it. And this is a very economics thing to do, differentials, by the way. So if you're doing finance as a combination of your degree, which I know a few people are, watch out. And theoretically, this would be what you would do if you couldn't separate your thing that looked like it might be separable. So over here, anything that looks like this can be written this way, if you want. The question is, are you able to have a method for solving this? And the answer is only sometimes. And here's the what if for this question. What if there was an unknown third variable which was a function of both x and y? What if u was a function of both x and y? Because if u was a function of both x and y, then here we go. A differential in u, a small change in u would be caused by both x and y changing. If x changed, then u would change. If y changed, then y would change. And the multivariable chain rule says that it will be some multiple of dx and some multiple of dy. So if I want to know how much u changes, I figure out how much x changes and multiply that by something, figure out how much y changes and multiply that by something, and add them together, it should tell me how much u changes. And this is the theory of how derivatives work. If you're extremely small changes, everything should work this way. It should be linear. And the correct thing to put in this spot is du on dx. And the correct thing to put in this spot is du on dy. And we have something that looks like this. It's here. So if there really was a secret function u that was a function of both x and y, then this should be du on dx and this should be du on dy. That's the reasoning behind it. And even more, du should be 0. And the only way a function can have its changes be 0 when you change it is for it to be constant, because it's not changing. This is the change in u, and if the change in u is 0, u is not changing, which means u must be a constant function, actually. So that is the whole reasoning behind it. So you go, oh, cool, if this is equal to 0, then u is a constant. That's the thinking behind it. And so, when we come back to this, and we're imagining that there is a function u that is a function of both x and y, and I know that if I do du on dx, and if I do du on dy, then this should be what's in that spot, and this should be what's in that spot. That's what I know to be true. And they call this usually m and n in the course. So this should produce m, and this should produce n. And I also know that if I differentiate this with respect to y, I will get du on dx, and then I'll get d on dy of du on dx of u. And if I differentiate this one with respect to x, I'll get d on dx of d on dy of u. And it shouldn't matter which order you do those derivatives, you should get the same answer. If I do u differentiate with respect to x and then y, I should get the same answer if I differentiate with respect to y and then x. That's a theorem. Almost all functions do that. And so this should be the same. This is the picture that this entire thing is based on. The functions in these spots ought to be the partial derivatives of some other secret function. And these two functions, if I differentiate them with the opposite variable, should give me the same answer. And this thing happening is called being exact. So in order to do this process, the first thing you have to do is differentiate this one with respect to y and this one with respect to x. And if you get the same answer, then you can do the process we're allowed to do. So step 0, do dm on dy and dn on dx. And if they're the same, it's exact. And if it's not exact, you give up and hope that someone else knows how to do it. Or if you're in an exam, you would say, I must have done something wrong. Or if it was an exam, you would look at part B and go, oh look, they're now telling me if I multiply everything by x, it should be exact. That was an exam question in the past. They went, is this exact? You do the calculation and you go, no. And then in part B, they say, now multiply everything by x. Is it exact now? And you go, yes, it is. And so you solve it. Yeah, just so you know. I don't know why you would multiply it by stuff. It's an integrating factor thing, but they don't teach you that. They just sometimes get you to do it. Okay, so step 1 is I'm going to run around this diagram. If I integrate with respect to x here, and then differentiate with respect to y here, I should get from m to n. That's how the process works. And so when I draw this diagram, it tells me what to do. I could go the other way. I could integrate this one with respect to y and come down this way, and it would work just as well. So you can do integrated m with respect to x, and that will produce something plus a constant which could involve y's. Because when you do this derivative this way, the y counts as a constant, and so anything involving just y's and not x's would disappear. And then that is what u has to be. And so then you do du on dy, and you get something plus c dashed of y, and that's supposed to be the same as n. And you compare this to n, and that tells you what the c dashed of y is, and then you can sub that back in here and it tells you what u is. And that's the end. And then the final answer is, and then so you go, now I know what c dashed of y is. It's whatever bit of n is missing. And then that allows you to figure out what c of y is by integrating that. And then you can sub into u, and you'll get u equals crap plus whatever this is, equals a constant. And what you've got when you get to this stage is, oh, a whole lot of things involving x's and or y's equals constant. It's an implicit solution. Just like before when we did this thing, and we got something involving y's and x's equal with an equals in the middle, it's an implicit solution. So this is an implicit form. If you are extremely lucky, you can rearrange this to get y equals. But no one is that lucky. And so they will say, write your answer in implicit form. And this happens in the Mobiuses in this course. People go, what do they mean by write it in implicit form? Go, I mean, write this. If they also tell you what the value of y and a matching value of x and y, then you can sub it in and it'll tell you what c is. So that's great. So I don't know if this is helpful. I hope it is. But this diagram tells me what to do. There is a secret u that when I differentiate it produces the m and the n. And if I differentiate them with the other things, they should come out with the same answer. And I can go up here and down here. And that means that you can technically imagine having one with 3 variables in it. There'd just be more up and downs involved. Not that they'd ever get you to do that in this course, but you know, it's nice to say, well, if I can do this, I can do anything. Now, I've really made the order not good. So we had separation, that was that. We had ODEs, we had first order separable. All right, I should really number them. Okay. So we're now at the end of this. We did this one, we did this one, we did this one. These ones are in Maths 1B, this one's new. But it feels, when you get to the end, not too dissimilar to the separable, and in fact, separable DEs are automatically exact. Because of stuff. Or maybe that's wrong. They can be turned into exact ones. Close enough. Okay. The difference between them is that when you do the separable one, your y's will all be on one side and your x's will all be on the other side. And so it'll be a whole thing involving y's and a thing separately involving x's. But when you do this one, all your x's and y's are usually multiplied by each other and they're stuck together and you can't separate them. So, yeah. But no one wants you to because they're happy for you to leave it in implicit form. Okay. That's first order. But I have one secret first order thing to add, which no one tells you about, but you really need to know. ODE first order linear, but with constant coefficients. So instead of having dy and dx is a function times y, it's just a number. And it's going to be homogeneous as well. Like that. Or even better, like that. Technically that would have been a minus ky if I did that move, but I just don't care. There's a number in that spot. This is so common, you should just know how to do it. The answer to this is y is k e to the kx. It just is. I mean, it's not, doesn't just is. The reason I can do this is a separable dE. I can move this y over here and have a 1 over y dy equals k dx. And that's separable. And I integrate both sides, and I'll get a 1 over y, that becomes an ln, and then have to do e to the power of to get rid of the ln, which is where the e comes from, and that's where it comes from. But also, this just says that the derivative of y is a multiple of the original, and that's exactly how e to the power of works. E to the power of kx, when I differentiate it, will be k times e to the power of kx, because that's how e to the power of works. And so that's just the kind of function that does this. Yep. No, I don't think so. Could be wrong. My caveat is, if this was a straight up equation and there was nothing else around it and it was just part A and they went, find this, then I would do the working. But if this turned up in the middle of a PDE question, then no, you don't have to show the working, just write it down. That would be my answer. And the reason I know that is because the lecturers did that. In the middle of their PDE questions, they just had this, and then they just wrote this answer down. So if they can do it, so can you. That's my answer. So, but if this was the entire question, and they just said, solve this, then I would show the working. Yep. Nope. It's only a first derivative, so there's not going to be two of them. But I will come back to that. Sweet. Okay. But I got all grumpy about it, but actually that's true in all courses, right? Regardless of whether they're maths courses or literature courses. The things that the lecturer does are the things that you are also allowed to do. And if they complain, you tell them, well, you did that. How was I to know? And example, this semester, one of the economics courses that has a lecturer who is famously hostile to student questions, they did an assignment and the students did exactly what she did in one of her examples, and she docked them all marks, and then someone put up their hand and said, but in this example, in example 1.7, you did this, and she went, oh, so I did, and she gave them all their mark back. So there you go, that's my parable of the day. So even a hostile lecturer will respond to, well, you did it. All right. So that's all our first order ones. Let's just make sure we've got the vibe. First order comes in separable, linear, or exact. Anything else? Sorry, it's going to be too hard. But most of them are of that flavour. And separable, we separate them. Linear, we make an integrating factor. Exact, we have to integrate up and differentiate down. And then sometimes if you've got a really nice first order separable, this is both separable and linear, basically. And the separable linear ones are really nice and they just have an answer. But only if it's part of another piece of working. Okay. All right. Woohoo. Awesome. And the reason I spent so much time on that is that every other question that these come up in, you just have to know. Like the exact isn't going to come up that often, but that last one comes up in the middle of other questions all the time. And there'll just be these times where they just expect you to notice that it's linear. And it happens in the PDEs questions all the time. When you separate PDEs, sometimes you get a first order one on one side, and you just go, you look at it, go, oh, cool, linear, integrating factor, this is the answer. And they just expect you to notice it. So you need to be able to notice, really notice what to do for a first order one. Right. All right. Right. Second order. We're still in ODEs, everything's ODEs now. Second order ODEs are not on that list. Frobenius is used for one of them. So second order ODEs have second derivatives in them, and pretty much you've only been taught how to do linear ones, as far as I can tell. Could be wrong. So feel free to just say, but what about this one? That's not of that form. But I'm pretty sure you've only been taught to do linear ones. Unless it just says d squared y and dx squared equals something involving x. Then you just integrate it twice. That's fine. So let's just do that one, just to be clear. I don't even know what the name of this one is. It's just an easy one. Y double dashed equals something involving x, where you just integrate it twice. And you'll get like, you know, this is just my example. No, I will not do that. Oh, yay. Y dash would be a half of x squared plus a third of x cubed plus c, and y would be a 6 of x cubed plus a 12th of x to the 4 plus cx plus d. Done. Always okay. And yeah, you could do a seventh order one if you wanted, and it would be fine. Yay. Okay, just pointing out that that's always there as an option, and never be afraid to just check if it's just x's, and you can just do it. Right. There's one integration will get rid of one dash, and the second integration here. So that's an integrate there, and that's another integrate there. Okay. All the other ones are linear. And linear ones always look like this. You'll have y double dash plus something involving y, something dash plus something y equals something. And the point is that these are the only y's in the equation. All of the y's are like this. And it might be written as d squared y on dx squared, or d squared y on tt squared, or whatever. It might be written that way. Just don't be afraid. So there are options for what this could be, like, you know, not a curly. I'm so used to curlies. D squared y on dx squared, or they might have written it as d on dx squared of y of x. That's another option for how they write it. They just like to mix it up. And the stuff in this spot may or may not involve x's. May or may not. Oh, it's totally linear. Oh, correct. It is linear. It's linear easy. Yeah, autonomous is when there's no x's at all. It's only y's. In Maths 1B, you did autonomous first order with phase diagrams. Do we have autonomous ones in this course? Don't think so. That's in D's for maths. Cool. All right, so linear ones look like this. And if this is 0, they're homogeneous linear. And if these are constants, then it's linear with constant coefficients. And you can be also linear homogeneous with constant coefficients. And all of them require their own slightly different methods. So here we go. I'm not necessarily going to go into too much depth. Linear, constant, coefficient. Actually, just even before all of this, there is one thing to know about linear second order DEs, whether they are constant crap ass. No, sorry, just a second. Homogeneous. So linear homogeneous ordinary differential equations, which is where we're up to now, where it's under linear still. And they are the ones where you've got, and there's a 0 in that spot there. linear homogeneous ODEs, or homogeneous linear, I can't remember which one traditionally goes first, have a theorem. And it doesn't matter what degree it is, it'll work for third order as well. There's a theorem that says that for second order, it doesn't even matter if there's stuff here as well, but it's tradition to divide that out. For first order or second order, okay. So for second order linear homogeneous ODEs, you will get, all the solutions will be able to be made from just two of them. That's the theory. So the theory says, and they borrow it from linear algebra, okay? So because functions are like vectors because you can add them and you can multiply them by scalars, and derivatives are like linear transformations because when you do add first and do the derivative, it's the same as doing the derivative and then adding, and that's how linear transformations work on vectors. So the way that derivatives work on functions is the same as the way that linear transformations work on vectors. And so we borrow what we know about vectors and we go, this is the kernel of a linear transformation and is therefore a subspace, and it therefore has a basis. And there's some other theory that says that because it's a second order, the basis will be dimension 2. And so this says that that given any two solutions, that are linearly independent, we'll call them y1 and y2, all the other solutions are something times y1 plus something times y2. That's the theorem. And if it was a third order, you'd need 3 of them. And if it was a fourth order, you'd need 4 of them, and so on. Yep, so given any two solutions, y1 and y2 that are linearly independent, all the other solutions are that. But we need to know what linearly independent means for functions, and that's what the Wronskian is for. It is sk and not kus, Wronskian. Yep. Not Ronxian. Is it sk or kus? I don't know. Sk? Wronskian, okay. So the point of the Wronskian is to tell you whether two functions are linearly independent or not. You can tell there are some lists of functions that are just guaranteed to be independent without you checking. And causes and sines are automatically independent, and so are so examples of linearly independent functions. Cos of 2x and sine of 2x are definitely linearly independent. And cos of x and cos of 2x are also linearly independent. So if you've got different numbers in these spots, they're linearly independent as well. And e to the 3x and e to the anything else x, they're linearly independent as well. Also, x and x squared are linearly independent, and any 2 powers of x are independent as well, x to the 5 and x cubed, they're independent. So just so you know, most of the functions that we're familiar with are independent from each other. I'm not sure about x and cos 2x. So if you're not sure, so any 2 powers of x, automatically independent. Any 2 e to the power of somethings, automatically independent as long as these numbers are different. Same with cos and sine, or 2 coses or 2 sines. If you're ever not sure, there's a test for it, and it's called the Wronskian. That's what that's for. So if you're not sure, then y1 and y2 are linearly independent if the possibly ks, and the Wronskian is this: y1, y2, y1 dash, y2 dash And if there were 3 functions, you'd go down to the second derivative to make a 3 by 3 matrix. And if there were 4, you'd go down to the 4th derivative to make a 4 by 4 matrix. So if you're ever not sure, calculate the Wronskian, and if this is not 0 for any one x, then they're linearly independent. That's a determinant there. If the Wronskian is not 0 for any one value of x, then y1 and y2 are linearly independent. So the thing is, the only way they can be dependent is if this is always 0 no matter what x is. So if, when you get your formula, it involves an x, then they're independent. Or if when you get your formula, it comes out to the answer 4 every time, then they're independent. The only time they come out to be dependent is if the answer is 0 and has no x's in it. Right, just want to point that out. Though there are some very crazy functions, if you do your algebra, will come down to be 0. So just make sure you do as much simplification as you can. Sweet, okay. But if it's possible for this answer to not be 0 if you sub in the right x, then they're linearly independent. It took us like a week at the Maths Learning Centre this year to figure that out, because the theorem that goes with this is written ambiguously, and we couldn't convince the lecturer that it was ambiguous. And I was trying to say, but the definition of ambiguous is that it has more than one interpretation, and we've interpreted it a different way. Hence, it's ambiguous. It didn't fly. I really thought it would. It's a yeah. And maybe he didn't understand, didn't believe my definition. That's usually the problem. Okay, so that's something about linear homogeneous. So, therefore, knowing this fact, if you have a linear homogeneous equation, all you have to do is find 2 different solutions that are not multiples of each other. Okay, that are linearly independent. And you don't have to do the Wronskian with 2 of them, because one's a multiple of the other, just like the 2 vectors. So what that means is if you've got linear, constant, coefficient, homogeneous, not constant, just linear at all. Damn it, David. There it is. Linear homogeneous. Then what you need to do is find 2 different solutions, y1 and y2, and then all the rest are something times y1 plus something times y2. There's no particular reason you have to use C1 and C2. You could use A and B if you want, use C and D, you could use alpha and beta, mix it up. Or not. The person who's marking it, it's better if it looks most similar to their mark scheme. But I tend to find that C1 and C2 get me into trouble later, because then I find something else that I want to call C1 and I've already used it. So, yeah. So that's the thing. So how do you find those 2 different solutions? That's the question. So here we go. There are 3 different situations in which you might in which you can find the 3 different solutions. So first, it's got constant coefficients, which means it's y double dash plus constant times y dash plus constant times y equals 0. In that situation, we do our fabulous, well, what if the answer was e to the power of something? What if it was e to the lambda x? And if it was e to the lambda x, if you sub that in and do all the derivatives, when you do the second derivative, that lambda is going to come down twice and you're going to get a lambda squared. And so what ends up happening is you create this characteristic equation, which is lambda squared plus a lambda plus b equals 0. And that'll give you 2 solutions for what lambda is. And I just said earlier that if you've got e to the number x and e to the other number x, then they're independent. And ta-da! Yay! So that's great. But what if they don't get 2 different answers? And so those who have trod this path before us have found the solution. So you're going to get two solutions. Lambda equals two answers. And those answers are either going to be two different numbers. So lambda equals, two completely different numbers, very often plus or minus something. And then you're going to have as your two solutions either the alpha x and either the beta x. And then you'll go C1 of this plus C2 of this, or A of this plus B of this, or whatever. And if your lambda comes out to be the same real number twice, then your two solutions will be e to the alpha x and x e to the alpha x. And if your two solutions come out to be a pair of complex numbers, then your solutions will be e to the alpha x cos beta x and e to the alpha x sine beta x. And there's all this fiddling around with complex numbers and crap that does that, but no one cares, just do this. People discovered this even before complex numbers, so, derivatives existed before complex numbers. And if you actually do it, if you literally sub this in to that differential equation, it will work. Okay, cool, and that's it. So some people tend to forget this and they go, oh, it's e to the alpha plus beta I x, but e to the I x, e to the I anything is cos thing plus I sine thing, right? That's the definition of what e to the I thing means. And that came up in the last assignment, last Mobius. It's something that they want you to never have far from your mind. And so it is not surprising if you get e to the power of complex number that there will be coses and sines involved. Unless you don't remember this. And you do need to remember that. So back in, if you learned complex numbers at school or in Maths 1M, they would have called this cis, like CISX. But now we call it e to the power of IX. And lots of mathematicians are really down on cis as a function. I think it's kind of pleasant, but anyway. Okay. And I never want you to forget this. It will come up. In fact, there is a really important place it comes up, which is in the middle of doing a separation of variables for PDEs. And there's a special case. Oh, I will say something. If it's a third order, you'll do exactly the same thing, and you'll get a cubic equation, and it will get solutions. And you'll get the real one will go with an e to the whatever, and the two complex ones will go with the e to the cos and sines. It'll all work fine. You just do the same things. Not that they're going to do that to you probably, but it's fine. Maybe in the maths version of this course they might, because they don't do the Laplace transform stuff, so they've got to do all the other stuff. So there is a special case. Y double dash is constant times y. And I'm going to make it even more, f double dash is k times f. This comes up in the middle of a PDE question. And you actually run through what would happen if k was 0 twice, which is this one, and what would happen if k was plus or minus something, which is this one. And so you end up with lambda squared equals k, right? And so you get, oh, okay, depending on whether k is positive or negative or 0, I get one of these three options. And that is where all of that comes from. So if k is 0, we get lambda squared equals 0, so lambda is 0, 0, and we get e to the 0x and x e to the 0x, which is 1 and x. And if k is positive, you'll get, and we make it equal to like p squared, is that how they do it? Anyway, it's a row, yes, yes. Sorry? Yeah, I know. It's a p in the Mobius, because you can't write the row. And then you go, oh, cool, the lambda is lambda squared is p squared, and lambda is plus or minus p. And so you get e to the px and e to the minus px. And if k is negative, you get k equals like minus omega squared. And so lambda squared is minus omega squared. So lambda is plus or minus omega I. And you get e to the 0x cos of wx and e to the 0x sine of wx. And they're 1. So that is where that comes from. It comes from here. It is totally okay for you not to put this e to the zeros in. The lecturer doesn't, but I just wanted to explicitly line them up next to each other so that you could see where they come from. And then in the PDEs, you actually find out that this one doesn't happen. And, you know, it's all good. But sometimes, usually this one happens. Sometimes this one happens and sometimes it doesn't. And yeah, it's always annoying when you get an X over here, which has only ever happened in one exam that I've known about for this course. This is the Sturm-Liouville problem. In fact, Sturm-Liouville. Is there an S in Louisville? But the Sturm-Liouville problem is this problem, but without the A there, right? And it's this problem, but not knowing what the K is. Yeah. And so whatever two answers you get, you end up with like, you know, A of one of them plus B of the other one, right? That's how you do it. Okay, cool. And all constant coefficients ones go that way. Somehow, it just has this wonderful property of just telling you what these solutions are. But in other situations, how are you going to get them? Where are we up to? We're still in linear, aren't we? Okay. So there is an issue that happens if by divine providence you have one of the homogeneous solutions but you can't find a second one, there's a process for doing that. So you know one solution is y1, but can't get a second one. So meaning we don't know what the y2 is, right? If you're in that situation, which does happen, I mean, sometimes they just tell you, here's a differential equation, this is one of the solutions, find the other one. But sometimes it does come up. There's a process for doing that, and it is called reduction of order. And in reduction of order, you say, what if the other solution was a function times this solution? I think that's how it goes, right? Do they call it u? It's tradition in maths to call another variable u. And then if you, theoretically, you could run through doing all the derivatives and subbing them in and stuff cancels out and you get to a place, but there's a formula they tell you for where that gets to. And what it gets to is it tells you a differential equation involving u. And it'll say something like u double dash plus crap times u equals 0 usually. No? Or is it something else? It becomes separable? So there's a 0 here. Oh, and you called w u dashed? Yeah, but then so along the way, somewhere in the middle here, w is u dashed. And so then you get an equation that has w dashed equals crap times w, and you solve that because it's now separable. Oh, probably. Is it equals 0? Oh, it's a plus. Okay, so it's tradition to have this, and then there's some stuff in here involving the things from the original equation. Okay, with the P's and the Q's and the R's and... Yeah, cool. There's something here. That's what formula sheets are for. Something involving PX's and Y1's. Yeah, okay. And then that's solvable, and you figure out that W is this, and therefore U must be the integral of that. And just don't forget where you came from. Therefore, Y2 is that answer times Y1. That thing. Right. And therefore, all the other solutions are constant times Y1 plus constant times Y2. That's the entire goal of this, to get to there. And I'm pretty sure that this process is what proves that this x needs to be here to get the second solution. So if you run through this process starting with e to the alpha x and do all of this stuff, you end up with x e to the alpha x as the other solution. So pretty sure. I wouldn't even be surprised if there was a video somewhere in the course that had that example. Okay, other than like you just believe us. So, okay, so what have we got so far? We've got, I just need to write it down again. So we've got linear, homogeneous, ODE, yep. And if it's constant coefficients, your y1 and y2 come from your e to the lambda x's, yep, and your characteristic equation. And if you've got a y1 but you don't know what y2 is, use reduction of order. That's what we've got so far. Yep. And no matter what you do, it's always something times y1 plus something y2 gets all the answers. So what if it's not homogeneous? Well, the theory for not homogeneous linear ODEs is that you solve the matching homogeneous one and you add all of its answers to any one answer you can think of for this one. So you go find all solutions to the homogeneous one. And your lecturer would probably call that the general solution. Yep. Yeah, well, it's a general solution to the homogeneous one. And that'll be of the flavour of C1Y1 plus C2Y2. And they normally call that YH. And then find any one particular solution to the original. It doesn't matter which one it is, any one will do. And that's what the word particular means. It means just one. So if someone just happened to tell you, this is a solution to this DE, you could just add it to the homogeneous one. Classic exam thing to do. You do the homogeneous one and then they just happen to tell you what the answer is for the other bit. And you don't have to find it yourself. So we have some problems. We know how to do this now. Good. How do you figure out the one particular solution? And you have two different situations that can happen in. So if you've got one particular solution, what do? Well, if it's a if it's a constant coefficient linear homogeneous DE, yep, then you try undetermined coefficients. how to get your one particular solution. So just a second. Constant coefficients. Yep. Then do undetermined coefficients. What that means is that if you've got a linear one, linear DE, like with your y double dashes and your y's and your y, equals function here, you look at what that function is and you say, what if it was like that, but with a different coefficient instead? And then you sub it in and differentiate it and you get equations and you figure out what the coefficients are. That's how it works. And there's a little table in the notes somewhere that says, based on the flavor of Rx, what you should try. And the table is quite difficult to interpret. So this is what I say, and you know what I'm going to say. You should include as your y Rx and anything that's in any of its derivatives. So if you had Rx, you had something like this, equals, you know, x to the 5, 7x to the 5, then you would try something times x to the 5. But you'd have to have the derivative of x to the 5 as well, which is got an x to the 4 in it. So you also have to have something x to the 4. And you have to have the derivative of that too, so x to the 3. And you have to have something x squared. And you have to have something x. And you have to have a constant. The derivative of that is 0, so I'm at the end. And these are all the things that I'll have to include. And these are what all of the derivatives of this thing look like. And then I don't have to remember. You just put all the derivatives of the thing you've got. And if it was a 7x to the 5 plus x cubed, that's okay, because the x cubed is already one of the derivatives of the 7x to the 5. It's already covered by the derivatives of that, so I don't have to worry about it. And cool. And if I had that, well, I would try y equals something times cos of 3x. But the derivative of cos of 3x is minus 3 of sine of 3x, so I'm going to have to include something times sine of 3x as well. And it tends to work. If I had x times cos of 3x, that derivative using the product rule would have an x, and it would have a cos of 3x by itself. It would have an x. It would have an x times sine of 3x, and I have to differentiate that as well, and so I would end up with a cos of 3x and an yep, I just might as well write it down. Don't just say it, David. You would. So if I had that, for example, then you would try y equals something x plus something, because that's the derivative. The derivative of x is 1. And then I would also include the cos of 3x and a sine of 3x as well. That's what you're asking? Like you just do this one and that one separately? Yep. And if they were multiplied together, well, the derivative of that would include a cos of 3x and an x sine of 3x because of the product rule. And the derivative of that would have a sine of 3x. And the derivative of that would have a sine of 3x, which I've already got, and an x cos of 3x. And there they all are, yay. So some people say, well, that's you could also do what you would do for this times what you would do for this, and that will also work. Because this is a plus bx times, because this would get to the same structure if you had a plus bx times c cos 3x plus d sine 3x. And you expand it out, you would get constants times all the same things. So you have a cos 3x and an x, and a sine 3x and an x cos 3x and an x sine 3x. That works too. But that's two separate rules, and I can only remember one, so I just imagine all the derivatives of the thing I've got and it will cover it. Just put them all in until you get back to things you've already got. And so that's just, it only takes me a couple of seconds to do it. And yeah, because in past assignments, at least Mobius is, or I don't know, there've been assignments where they've said, what form should the undetermined coefficients take? They don't actually get you to calculate it. And so you just, well, write it all down, A, B, C, D, E, F, and until you run out of letters. Yay. It is one of the things that I'm most proud of figuring out. No one told me this. But you need to put them all in, because to sub it into here, you're going to have to differentiate it. So the derivatives have to be there. Yeah. So, okay. That's linear, constant coefficients. What if the coefficients aren't constant? Well, then you do variation of parameters. You know, y1 and y2 for the homogeneous. Can't get yp for the original. That's okay. You know how all the solutions to the homogeneous are something times y1 plus something times y2? What if the somethings weren't constant? Oh yay, another what if. And these are both functions. And so if you differentiate it and you sub it in and blah, 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 there is a formula for what u and v are. I think you get u dashed equals something, and then you have to integrate it to get what u is. And similarly for v dash, and there's a Wronskian in there somewhere. So there's a process and you get u dashed equals something with a Wronskian on the bottom. Can't remember what it is. I think it's r times y1. One of them is r times y1, the other one's minus r times y2. Again, I can't remember which one goes with which one though. So which one's which? And this one's y2r? Cool. And it's essentially, actually, this Wronskian thing here is essentially solving a system of equations. It's just that the coefficients are functions, and so the determinant is a Wronskian. So there's an extra assumption in there. You actually assume that y dash y1 plus u dash y1 plus v dash y2 is 0, I think, along the way. Something like that, which is, I think, a power move, right? So it's like, oh, what if this? Crap, I can't figure it out. Well, if this was 0, then I could. Yay! It's just stupid, but also really clever, right? So, so you can see, I can tell now, I'm at this point going, oh my goodness, no wonder everyone's confused. There's so many different pieces of this course. And they're all like, and if this situation, but then this situation, and what I really want is a big thing with all of them in string, right? So that I can figure out how they're related to each other. And if I'm in the right frame of mind over the next few days, I'll try and draw one. In a couple of days' time, if you don't hear it, like, well, the video for this might not be ready until Tuesday, just warning you. But if when I send the email with the video, I don't include the David's diagram of the flowchart, email me back and say, where is it, David? I've tried to draw it before in 2018, but I didn't do a good job then. But I have to say, I'm really liking just having them all in the one place. Because when you flick through the notes, everything looks the same. There's just dashes and U's and Y's everywhere, right? And if you're not paying attention, and even if you are, it all just looks the same. And the human mind seems to just ignore maths, right? When you're reading the text, you say, I'll just skip that bit. Which is what you're taught to do in your physics classes, right? You go, here's the maths thing that tells why this is true. We'll just skip that bit. Doesn't work so well in a maths course. It will be on the Maths Learning Centre website, but I'll also email you all when it's done. Because I have to do it manually because I'm not part of the Echo 360 for your course. Yeah, if we're lucky, it'll happen by tomorrow. Like tomorrow night. It depends on whether the video processes in time. But I don't guarantee anything less than 2 work days. Okay, so just a second. So here's a question that we haven't answered yet. All of these are like, suppose I had one of the homogeneous solutions. Or suppose I had both the homogeneous solutions, what would I do then? How do you get them in the first place? I mean, we know how to get them in the first place if it's a linear constant coefficient differential equation, but what if they're not constant coefficients? That's what Frobenius's method is for. Yay! Here we go. Here we go. Last thing. Linear, not constant coefficients. Coefficients. ODE. Not necessarily homogeneous. Actually, no, it is going to be homogeneous. Okay, it has to be homogeneous. It won't work unless it's homogeneous. That's okay, we know what to do if it's not homogeneous. We use variation of parameters to get the particular solution. Or we make a really inspired guess. Okay, so the ones that we're going to be interested in are the ones that have polynomials in all of these spots. So maybe to have x squared plus x, or x times x minus 1, or 2. That's a polynomial as well. Polynomials in all of those spots. I'm just going to ask a word. Does the phrase Euler-Cauchy method?
Yes.
Too many methods. Just give me a second. That's the wrong course. Oh, I don't have it on me. I was going to search for it. Now I've lost Zoom. Fuck. Right, we're here. Okay. All right. So, the 3 methods that we're going to talk about go with this situation. And there is, I'm pretty sure, one that only goes with this situation, if I'm lucky. Ax squared times y double dash plus bx x times y dashed plus cy equals 0. That one.
So that polynomial is of the same order as the
Yeah.
group.
Yep. But it's not even allowed to have a plus x in here as far as I know. It's just x squared. And if it was a triple dash, there'd be an x cubed to go with it. It's okay, it will work if this is an x cubed and an x squared and an x. Probably. Because you just divide by the x anyway. But, like, okay. So you will try y equals x to the power of n for some n. For that specific case. This is the Euler-Cauchy, is it? And what will happen is the second derivative of this will be have x to the n minus 2, and when you times it by x squared, you'll get x to the n, and you'll be able to factorize out the x to the n. So what will happen is you'll get something in there which involves a and b and c and n, right? And that will be equal to 0. Probably have an n squared in it actually. And that'll be a quadratic equation that will give you 2 answers for n. And so you'll have x to the alpha and x to the beta as your 2 answers. If they're complex numbers, woe betide you, there'll be like ln's and coses and craps and stuff in there. So. Yeah. Okay, and this is based on the concept that when I differentiate a polynomial, the power goes down by 1. So if the power goes down by 2 and then I multiply by x squared, it goes back up again. And that thinking is what the other methods are also based on. Except instead of only having one x to the n, we have all of them. Now, just a second. The power series method works when... Okay, I've got it. Just a second. So, there are 2 choices. What might happen is that x equals 0 might be a singular point. And if you're lucky, it'll be a regular singular point. Or it might be an ordinary point, and then we'll be good. So if x equals 0 could be an ordinary point, and we'll just talk about what they mean. If you do this, you'll try y equals n equals 0 to infinity of a n x to the n. And if x equals 0 is a regular singular point, you'll try y equals n equals 0 to infinity a n x to the n plus r. And if x equals 0 is an irregular singular point, I have no idea what you do then. So it's not in this course as far as I know. If x equals 0 is an irregular singular point, you'll try x equals 1 and you'll do everything with x minus 1 to the n instead of x's to the n's. But yeah, okay. And this is called a power series method, this one. And this is Frobenius's method. And, well, that doesn't have a method, so it doesn't need a name. Abandon all hope. Here be dragons. So, that is what they are for. So just stepping back, linear DEs, polynomials in the spots next to the y and the y dashes, and we have to figure out whether it's an ordinary point or a regular singular point, and the only way to tell that is to rewrite it or singular and or regular, you have to rewrite it as y double dash plus px y dash plus qxy equals 0. And I think you multiply this one by x and this one by x squared, and if they both come out to be analytic, then it's a regular singular point. Something like that. I'd have to look that one up. There's a thing you do with these functions. But if both of these are defined for if either one of these is undefined for x equals 0, then it's not a regular, it's not an ordinary point. So if px or qx is undefined for x equals 0, then it's a singular point. They call it analytic, but in this context, it basically comes out to be undefined. So that's fine. So basically, these functions, if when you do the division, if they've got x's on the bottom, that's going to be a problem. But if it was x minus 1 on the bottom, that'd be okay, because x equals 0 isn't a problem there. It does mean that 1 is a singular point. And I think there's a thing where if you multiply one of them by x squared and the other one by x, and if they become defined then that's a regular singular point. But I can't remember which one is which. I'm pretty sure this one x and this one x squared. Could be wrong. So I'm pretty sure times x and qx times x squared, both defined, basically both polynomials, then it's a regular singular point. Pretty sure. Seems right. Yep, and so if it's not a singular point, ordinary power series. If it's a regular singular point, use Frobenius's method, and if it's an irregular singular point, give up. Find someone who knows more. Or maybe you already know the answer because it was constant coefficients anyway and you shouldn't be doing any of this. Okay, and the reason we have to worry about these x squareds and x's is so that when you sub it into here, everything works neatly. So what you're going to do in either of those cases is you're going to go y equals n equals 0 to infinity a n x to the n or n plus r, and you're going to do y dashed equals, and you're going to do, and this has got an x to the n minus 1, and y double dashed equals, this has got an x to the n minus 2. And then you're going to sub it in to the polynomial, and you'll get this great big power series with a big coefficient for x to the r, x to the n, or x to the n plus r, and it's equal to 0 on the right-hand side, which, so you're going to sub in and you're going to get all sorts of crap times x to the r, n, or x to the n plus r, or whatever it is, and that's going to be equal to 0, and therefore this is 0. Yeah. Right. I think that is the last method. I'm pretty sure. Didn't expect it to take that long. I have secretly booked Flenchy on Thursday next week. If you want another one, it would have to be at 9. Yeah. You okay with that? I'll send an email. If I forget by tomorrow to send the email, remind me. I'll write it on my hand. I know that 2 days out from the exam is cutting it fine. So there's a chance that the video won't come out, so you'll just have to do it live. But you can always come to the drop-in centre, but that gives you a whole extra hour of me time before the drop-in centre opens. So cool, just booking it in now, okay? D's for Eng, Thursday, So a week from now, right? But on the 9th. Okay, before I go, I mean, you guys can go at any time, but I did want to say one thing about organising your working for this, because it's really important to me that you know this. This one will be horrible, and I don't want to go all the way. I just want to point out how this works. So if I divide by this, here and here, neither of those have a problem with x equals 0 on the bottom. And so I don't have to use Frobenius' method, I can use an ordinary power series method for that. So just, that's the decision-making process. So x equals 0 is not a singular point. So I'm okay. But this version here is not the version we're going to be using to actually do the process. We're going to go back to the version where they were polynomials. It's really important or the process doesn't work. You can't do it from here. You have to do it from here. So that's my decision to say y equals a n x to the n. So I'm just going to leave some space. Am I going to leave some space? No, I'm not. So in this version, traditionally, you make this start at 1 because the constant term will disappear when you do the derivative. You don't have to do that, but it is a thing. Like, because if n is 0, you're timesing by 0 here. And so when n is 0, there isn't anything there. And so, yeah. Okay. So it's okay to do what I'm about to do. It just makes your working a little cleaner. You don't have to have some signs floating with pluses between them all over the place. You can figure out each bit separately. X squared times y double dashed, because that's from here. X squared times y double dashed is one of the things I have to do. And if I times this by x squared, that'll go back up to n. And then just leave a little gap in case you have to shift things over. And minus 1 times y double dash, we've already got what that is. And so that's from this, the x squared and the minus 1. This is the same as x squared plus x. So I'm going to need an x squared times the y dashed as well. So it was this, and I times by x squared, so that minus 1 went up 2 to a plus 1. And x times y dashed only went up 1 to an n this time. And minus x times y is that, because the y was this, and I times by minus 1 to get the minus, and I times by x to get an n plus 1. And finally, minus 3 times y. And I know this is complicated, but most of them aren't this complicated. And the reason I've done this is that when I look at all of these at once, I can now see, because they're above each other, much more easily which ones are n-2s and which ones are n+1s and which ones are n's. And I can see which ones of them to switch. There's like 3 n's in here. So I'm going to move this one to n and this one to n and this one to n. But if there were more n+1s than n's, I would move them all to n+1. And then at the end, you'll say the coefficient of x to the n, and you won't, they'll just all be lined up. So just add all the bits together without the sum and without the x to the n. Yeah. If you want to see me doing, yep. You can shift them backwards because it doesn't, there isn't, because the a-1 is going to be times by 0 anyway. Yeah, that's why. And this is what I was saying here, that when n is 0, there isn't anything there. So this is in fact the same as starting at 1. Because if you start at 0, the first term is a0 times 0. And this is the same as starting at 2. And so when you actually do these things, you can say for the double one that this one starts at 2 and this one starts at 1. And so shifting it back 1, that's going to be a problem, this one here. You're right, but it's okay. It'll be fine. It'll just prove that a0, there'll just be a coefficient that has to be 0 at some point. It's okay to shift them back. But usually this is what solves the problem, making the 2's there. Because there isn't an a, because it only starts at 2, there isn't an a-1 because it doesn't start until 2 anyway. And so there's an a2-1, which is a1 anyway. Yeah. Cool. This one is a problem, but it's fine. That's all right. You just won't include that one. That's okay. So in the Frobenius's method, like even in this one, you're going to have to treat the numbers that aren't in every sum differently. So in the Frobenius's method, it's really often true that some of the sums start at n=3 and the other ones start at n=1. And you'll choose the earliest n that appears in any of the sums, and you'll only pick out the sums that appears in n=1, for example. You'll only pick out the sums that appears in, and that forms the indicial equation. And then if there's any others that don't appear in all of them, then it'll have their own little equation of their own. And then at some point, you'll get to a point where all of the sums have that number. So with these ones, all of these sums, n=2 is the first time where all of the sums have that number. And from that point forward, then you can include them all. And that's where the recurrence relation comes from. So if you want to talk more about Come to Maths Learning Centre, it should be in some of the old revision seminars too. So I fully expect if we do this in a week's time, I'll have all the technical detail questions, and that's fine. I will just take questions, and what the best plan is probably to say, here's a question I couldn't do, how do I deal with that? But whatever, take it from how you want to do it. Thank you. I hope that was useful. I talked a lot. And I will try my best to put that together into some sort of handout that lists them all before your exam comes. Yeah, I'm going to stop the recording.